Okay, so Professor Shankar actually reached out and said that I should cover aspects of NoSQL and really the context of big data and what you're seeing in the industry today. Really how does it map to the kind of business use cases you're seeing today? Where is it that you see more traction? And really from a management perspective, how do you sell? I try to get into the aspects of selling and aspects of what we need to look at from an industry standpoint. Can I just, quick show of hands, how many of you have worked on NoSQL in this room? Anybody who's worked on NoSQL? Yourself? Which technology of NoSQL did you work on?
Mostly
Hive, okay. From the query perspective, okay. So you would have used HBase, I would think, right? Anybody else work on NoSQL?
Mongo.
Mongo, okay, great. And sorry?
It's part of the applications.
Okay, awesome. And Hadoop, how many of you work on Hadoop here? Anyone? Okay, great. This is going to be a lot of it is going to be basics today for people who are not familiar with NoSQL, the technology. I intend to cover technology aspects of it. That's what Professor Shankar asked me to cover. If there's anything else you want me to cover from an industry standpoint, I'm happy to cover that. I've been in the industry for around 17 years, let me just change the slide. Over the last few years, I've been in NoSQL. I work for a company called Aerospike right now. Anyone has heard of Aerospike in the room? No one. Okay, that's good. So it gives me a chance to sell you guys something right now. Before Aerospike, I used to work for a company called Mongo, which is a competitor of Aerospike. Mongo is a completely different type of NoSQL technology compared to Aerospike. Okay, we'll talk about that as well. In terms of quick introduction, in any guesses what these numbers are here, by the way? What's that? My statistics? Right, it can't be my weight or something. But anyway, so that's actually the number of employees of an organization that I work for, okay, which is actually decreasing. I just found that, I was thinking, what should I put in this slide? And then I realized that every organization I work for is decrementing in a big way, right? It's an exponential decrease, right? Start off with IBM a long time back. I worked for IBM for 10 years. After doing my PGSM, I moved into a market development role in IBM. And from IBM, I moved to Oracle, which is 120,000 people out there. I started of enterprise, selling in enterprise and working with various levels of an organization, enterprise company, which might be very, very familiar for a lot of you out here. And then I got an offer to move into a quote-unquote smaller organization, much smaller organization in Mongo. And in Mongo, I did a role of director for solution architecture in Asia Pacific. I was selling into the entire Asia Pacific market. And then I moved into a much smaller company compared to Mongo, which is around 60 employees worldwide. So talk of thrills of having worked in a smaller company, that's an example of it. It's a lot of fun, I tell you. People who have worked, anybody who's working in a startup right now or have worked in a startup? Okay. So ours is almost a startup. I wouldn't call it a startup, but 60 employees, give or take. You know how it is, right? The culture is very much a startup-ish culture. It's been great. I moved from an enterprise role to an open source and a quote-unquote new age technology. So there's a lot of learnings that I've got from an industry standpoint. And a lot of it is where the industry is moving as well. In some sense, if you look at the enterprise companies today, the SAPs of the world, IIMBs of the world, Oracles of the world, they're having to reinvent themselves. In fact, I'm reminded of a quote by the founder of MongoDB called David Echeria, who says that today's technology is all about enterprise companies trying to be startups and startups trying to become enterprises. So that's the challenge for all of us. How do we scale up or scale down and make sure that we're relevant, right? Because you can't become a big white elephant and not stay relevant. You got to move very, very quickly. Okay. In terms of my other interests, I'm into badminton. I spend a lot of time in the daughter, which is why I called it out at the very top. Do a lot of reading as well. Anyway, so let's start off with NoSQL, the technology, and really the context to it all. Okay? I find this a little weird to just. Oh, I need to wear it. Is that better? Okay. Is it audible? Is it better now? All right. So I'm sure a lot of you are aware of this. If you go back 60 years, 1956, I'm sure some of you have seen this picture. Right? It's not something new. That was the size of a server back then, right? huge in size. You need a plane to pretty much carry that server. It's an IBM 350 hard disk, 5 MB of storage. 5 MB? None of us talk of MB these days, right? And the system cost, interestingly, is $160,000, right? And just a context to today's systems, today's powerful, even the most powerful system that you can buy is going to be less than $160,000, right? So that's the context to where we're talking about. This is when 1956. Go forward a few years, 1980. We're talking of IBM 3380. Back then, obviously the most powerful system back then. 1 GB of storage, a lot in the 80s, and the cost of which is $50,000. So again, as you saw with my number of employees chart, you see that the cost is going down, and the power of each system is going up as well. And this is like exponential growth. Nobody would have even guessed it would be this very transformational in some sense, right? And then you look at what's happening today. This is again last year, and we're talking of 1 TB of storage. A lot of us already have those drives. Very, very cheap compared to what it is, right? So the cost of this is, really look at the cost out here. $160,000 to what we're talking about today, right? There's a drastic decrease in terms of cost, and the capacities of which have gone up humongously as well. So one of the things to remember here is, if you talk of any relational system, talk of the applications or systems built in the 1980s or 70s, they were built at a time when what hardware was? What was the thing about hardware back in the 70s or 80s? Sorry?
Really bulky and
expensive, right? Bulky, yes. I mean, obviously size is one thing. In fact, talk of a joke, right? I used to work for Oracle, and has anybody heard of Exadata or Engineered Systems? Or you work for Oracle? You work for Oracle? Okay, so anybody who's seen this Exadata box, right? It costs over $1 million. I don't want to badmouth it because I used to sell it back then. But the honest truth, it's a great box. It really works really, really well. It costs more than $1 million even today, right? And we had a case where we sold it to a customer, a big enterprise company. They couldn't get the box inside the room, inside the data center. Why? Because it's too big. And they sent us a mail saying that, hey, your box is great, we're trying to put it inside, but we're not able to get it inside. What do we do? The size of the door is smaller than the size of the Exadata box. This really happened. So one of our engineers who was a physicist, he looked at the dimensions of the room and the door and the box, and he sent a mail saying that bend it at this particular angle, and you'll be able to take it inside. Anyway, jokes apart, this is the reality of what we're talking about. This is where technology was back then. And this is even today's technology, right? We're not even talking about 50 years back then. So the cost of storage has gone down drastically. And we're talking about back then, when you look at the assumptions made, when these relationship systems such as Oracle or Sybase or these kind of databases, obviously they worked for a lot of years, but they were built with the assumption that storage is extremely, extremely expensive. Right? And some of you would have heard of normalization. Familiar? Yeah, so very familiar. Most of us would have at least in some form or shape brushed, normalization in some sense. And that has happened because you wanted to make sure that you optimize for storage. You didn't want to make sure that if you had a lot of data stored, you want to make sure that in some sense you bring down the footprint of storage. Okay, so this worked in the 2000s, right? You look at this till the 2000s when storage was very expensive. This was what was in vogue, right? Make sense? Okay, so things started changing. Obviously, again, going back to what it was in the 60s and 70s when these relation systems were in vogue, we're talking of, in some sense, making sure that you get all the data that you can, and before you even get the data, you filter it. Why do you filter the data before storing? So let's look at a newspaper. What do you do in a newspaper? Does it have all the information that you want in a newspaper? No, it's a push, right? You're going to get whatever you're given. Why is it that a newspaper has some limitations? Sorry?
Limited space.
Limited space. Exactly the same thing with a relational system. Because of the fact that you wanted to optimize for storage, you wanted to make sure that before you even get the data into the database, you make sure that you filter the data. You get only as much as you want to store. Right? I don't know if you've read this book on big data. I'm sure Professor would have recommended that. But there's a book where I forgot the name of the author, I read it recently, but he talks about how you have to make sure that you get all the data in today's world. You don't know what you're going to get out of the data, right? So it's important to store all the data that you can possibly store, be it in the Hadoop system or the NoSQL system that you're talking about, because you don't know what's going to become relevant tomorrow, right? So in some sense, those assumptions of the 60s and 70s don't hold water anymore. You can't filter the data, pre-filter the data before storing, because you don't know what use cases you're getting into. Make sense? All right, so Obviously, what has changed over the years, something that all of you are very familiar with. A lot of you would be using AWS. I don't need to ask you for a show of hands, but I'm pretty certain that at least 50% or above out here would have worked on AWS. So this has changed the game, right? I mean, you don't want to call it AWS alone. I mean, obviously Google Compute or Azure or any of these platforms that we're talking about, they have changed the rules of the game. In some sense, the cloud computing wave that we are seeing today has changed the game completely. What has it done? It has brought down storage costs in a big, big way. Right? In fact, for all of us, it's affordable. If you want to do a startup today, the cost of starting up is really, really low. Right? You can really start off very quickly, try it out, and see what's the and what kind of adoption you're seeing in the market. In the past, just to invest into IT was huge because you had to buy hardware, you had to make sure there's a lot of upfront cost that was involved. Today, that's not the case. It's changed the rules of the game in a big, big way. Okay? All right. So we talked about this. Obviously, that means implications of which is there's no capital expenditure. We're talking of data center in the box. I don't know if any of you have heard of this, but today you have a concept where the data center investment that used to happen in the past is no more the case. Even if you want bare metal, you can get bare metal on the cloud today. Any vendors come to mind where you can get bare metal on the cloud? Folks from IT, any cases? Any platform that you can? Sorry? Rackspace, it's more of a private cloud, but if you want bare metal, AWS doesn't provide you bare metal as of today, right? You have to procure what they have. If you look at software, for example, software gives you an option where you can have bare metal on the cloud. In fact, AWS also is going to introduce this. Oracle is talking about it. So bare metal becomes very relevant. Why do you think bare metal is important? I'm just deviating a bit, but just to get a little bit of a thinking process going on. Why do you think it's becoming relevant today to also have bare metal on the cloud? What do you mean by bare metal, first of all? Okay, well, his question is what is bare metal? Anybody can help him?
Physical servers.
It's basically physical servers, like what it was in the past. I mean, we're not talking virtualized instances. I mean, you can virtualize on top of it. So when I say virtualize, what I mean is, I have a server right now. Let's say I've got a laptop, and let's say the laptop's capacity is 100 GB, right, from a memory perspective. Now, if I'm the only guy using it, then obviously it's pretty certain that I won't be able to utilize the complete power of the particular software or particular hardware that I have. So how do I make sure I optimize for it? Is a virtualizer. So I make sure that the entire room uses it. I mean, it's a bad example, but in some sense is what I'm trying to allude to. So all of us can use it, where I make sure that everybody gets 2 GB of memory or whatever. So we virtualize the instance to make sure that many people can use it, right? To memory, compute, whatever be the things that you're talking about. So in some sense, that really rode the wave. That was really the cloud computing wave. It started off with virtualization, ended up being the cloud thing. But the problem with virtualization and cloud computing in some sense was, and you look at AWS, is you're not guaranteed bandwidth. Okay, what do I mean by bandwidth? If I have 2 servers running in a cluster, or if I have a client and a server, am I assured that I'll get 10 GB PS, right? No, the answer is no. Because AWS, if you look at the, I don't know if anybody works in Amazon here. Anybody works for Amazon out here? So I should be careful about it. Nobody, okay. So, and this is true of most cloud providers. You're not guaranteed any kind of network bandwidth. Regardless of whether you go for provisioned instances or high-end instances, you're not guaranteed bandwidth capacity because you're going to be sharing it with a lot of other users. Now, what does that mean? If I'm a company like Snapdeal or Flipkart or any of these big companies which are growing at scale, that's going to become your bottleneck very, very soon. So you've got to make sure that in some sense, I give him dedicated instances or dedicated network so he can play around with it. So that's really where the industry is moving towards, right? Bare metal on the cloud. It's still cloud because I'm paying it as I use, but it's dedicated for me and I'm going to use it as I want to. Okay, makes sense? And that's why software and these products are becoming very cool. I mean, Oracle as well is talking about it right now. So. All right, so we talked about filter, store, and distribute. Remember the newspaper example? What we're talking about today? Sorry, go ahead.
So, I mean, it's not going to amortize. Basically, virtualization is amortizing the cost across multiple
That's right.
But in bare metal, they're not going to amortize. And still, the person pays for how much ever he uses. How are they going to make?
Yeah, so the answer to that is you're right when it comes to something like a startup. If I'm a company like Flipkart, I probably have 100 different business units that can use my own hardware. But I don't want to take the upfront cost of investing in hardware, or I don't want to take the cost of making sure that or I don't want it to be available to the public internet. I want it to be dedicated for me, right? So in some sense, The offering is, I give you bare metal, play around with it, give me as you use it, right? You pay me as you use it in some sense. And that guy is, it can either be dedicated for you, or you can still share it with other users as well. So that concept still holds good. Okay? So coming back to the concept in terms of NoSQL and this larger big data ecosystem that I'm alluding to, we're talking of a concept today where I want to get all the data, n is equal to all. How do I process every single data point that's available? A famous example, you guys would have heard it many times in B school, is the beer and diaper story, right? I'm sure you've heard it, right? Anybody has heard the story? The beer diaper story, right? Very common one. It's still something which amuses me, but just to give an example, people who have not heard it before. So the example is on a Saturday evening, what this particular superstore in the US found was, they found that there was some kind of strange correlation between diaper sales and beer sales. Right? So they obviously, how do you do that? You look at every single invoice and you find that there's a very strong correlation between beer sales and diaper sales. Why do you think that's the case? And he cannot guess, but anybody else can. Why do you think there's a correlation between beer sales and diaper sales? Guesses?
So Saturday evening you have beer and probably have to take care of it.
Do you have a kid? So he knows the trick here, right? It's the same with me as well, right? So the point is, the wife is tired of taking care of the kids on Monday to Friday, and she says, okay, I'm done with Saturday and Sunday, you got to take care of the kid, right? So the husband thinks of, okay, this is an opportunity for me to get some beer cans home. Obviously, you need diapers because you need to take care of a kid. So they found that there's a very strong correlation between the fact that there's going to be beer sales and diaper sales as well. And this is a real use case, right? You can check it out on the internet as well. How did they do this? And that's the point I'm trying to get to, right? They did this because they could analyze every single data point. They could look at, if you have 150 different items in your invoice, how do you find correlation between every single one of them? Right? You require a huge amount of computing power. More so, how do you store it? Where do you store it? If I'm talking of a relational system, how do I store it? It becomes extremely difficult for you to store it and then process it. You can't run Hadoop jobs all the time to find this data, right? To find the patterns of correlation in data. So it becomes very, very critical that to analyze data on the fly. And today we're talking of Spark systems and real-time systems where you can analyze data on the fly and make sense of what's happening from a business standpoint. Right? Make sense? So really what we're looking at today is store all the data that you have, filter it, and then actually distribute it to the world. Okay, this is where NoSQL comes into being in some sense. All right, so some more numbers. I talked about Oracle's appliances or engineered systems. Look at the numbers out here. This is again dated 2010. Facebook Facebook by itself had 13 million queries per second that it had to process. This is 2010, so obviously it's changed in a big way now. But regardless, even if I go back 5 years or 6 years, you'll find that with the capacity of even the top 10 database appliances, each of them costing more than $1 million each box, right? They could only do, look at this, right? If you divide by 60 because it's transactions per minute, we're talking of 500,000 transactions per second. That's all that an Oracle system could do, a supercluster Oracle box could do. Likewise, if I take the top 10 most powerful hardware systems on the planet right now, all it can do together is lower than 13 million transactions per second. So I'm investing more than $10 million in some sense, and I still cannot do what I would need to process. So this is just Facebook's example. But you look at any one of them, Twitter, or any one of these huge data kind of companies, it's about how do I process massive volumes of data. And clearly, relation systems or the kind of massive systems that we're talking about cannot process this volume of data that's required. Make sense? All right. So we're coming back to the same thing that some of you would have already seen this, the 3 V's or 4 V's. We're talking of really velocity of data, how fast can you process the data, different types of data. Can you give me an example of different types of data? Sorry? Sure. Different types of data. It could be textual form, it could be data which is time series data, it could be media files, it could be video files. There's a lot of data out there. Look at YouTube, right? There's so much of data, and it's still not a problem that's been solved. How do you make sense of the data which is stored in YouTube? All of us use YouTube. Can I make sense out of that and then start selling people some kind of solution? So that's where a lot of the future solutions are going to be. Video data. I'm sure a lot of you will be working in that space as well. So how do you process data of different forms in some sense? And then lastly, volume. So this is a given, right? We're talking of data which is growing 90% every year, or really doubling every 2 years, right? So that kind of a thing we're talking about. And obviously, you should be able to have systems that can process massive volumes of data. Fair enough? Okay. All right. So this is a survey which was done in the US. It was done to find out what are the areas in which big data firms are actually using, rather how are companies using big data, right? And what you find interesting out here, the reason I brought up this chart is, you'll find that majority of the use cases where big data is being used is not really for volume of data. It is for diversity of data, which means that people are using big data more so because they have data which is changing very often. Right? I'll give you an example, right? Why does it change? Because your business is changing. Your business is changing really, really rapidly. I'm pretty certain that a Flipkart or a Snapdeal cannot guess what's going to happen in the next 2 years in India. Because there's a massive retail growth in India and nobody knows where it's going to take off or where it's going to go in 2 years' time. So you have to have a flexible way in which you're going to store data. If you are hard-bound by your database, God save you. Right? It's not going to work because database, if you remember the time when, anyone of you here has worked on the relational databases such as Oracle or Sybase or DB2? You have, right? Have you done any kind of transformation program for your customer or something? Okay. How about yourself? You have? So what's the biggest challenge there? What's the biggest challenge when you're trying to do something new on a relational database system?
Quality of input data.
Sure, quality of data is one thing, but what's the biggest thing? What's more important than quality? What's the cycle for you to be able to implement that? Let's say you want to make a change. How much time do you think it would take in back then? We're talking anything between 6 months to 9 months, just for the implementation cycle. For all that we know, 6 months is way too much today. It doesn't work, right? You can't wait for your business. You can't wait 6 months to introduce a new feature that's required right now, because business is changing really, really rapidly. That doesn't work. And the reality is, while that changes, the types of data is changing. So we're talking 65% of use cases of big data where diversity is the key thing, or variety of data is the key thing. Okay? So that just to give you a sense of big data being more relevant from a variety standpoint than volume as well. Okay? What's this? Relation guy. I think you can relate to this. What is this?
Schema.
What's this? It's a schema. Okay. It's called an ER diagram or whatever, right? And it looks like cow poop or dog poop or whatever, right? This is the reality. It used to be this bad back then, but even now it is. And the honest truth is, if you look at this, you can't make sense out of this, right? It really looks completely haywire. You just can't make sense out of it. Obviously, the whole idea was to make it more easy for people to come in and understand what's happening here. But the reality is, for you to understand this takes you at least many, many days to understand what's happening in these things, right? So this is the reality. This is an actual chart from a customer implementation, right? And what's the biggest challenge here? If I want to make a change to that particular schema that we talked about, right? What are the changes that you have to do? Sorry?
You need to work on dependencies.
Such as what? Dependencies such as what?
When a schema change on one may have a direct impact on another point here.
Sure. And what about the implication from a application standpoint? What's the implication from the quote-unquote SQL layer? So many changes. Go ahead.
Queries that are
Queries. Everywhere there's going to be an impact. Right? So one small change in the database has an implication going up to the application tier and probably the network tier everywhere, right? So it's a humongous impact. And that's the biggest problem. To make even a small change takes a lot of effort. Okay? And this is why businesses are changing today. Alright, so if we're talking of really code changes, some kind of object relational mapping change, I don't want to get into too much of technology jargon, but essentially you have multiple changes for just a simple database change. Okay. Alright, so essentially what we're talking about, if I have to add a new table, have to alter table, I don't know if anybody is familiar with SQL out here, but if I did something like an alter table, I want to add a new column, just that small thing has a huge amount of effort, because I need to make sure that my, the object that I have in the application has to be changed. There's a lot of impact for every one of these things. It's not simple to make any change. It's all fine to do the design at the very beginning and have all these logical data model, physical data model. I don't know if some of you have worked on that space, but it's all great to do that. But then to make a change later on, it's extremely, extremely difficult and complex. Alright, so net, the challenges of relational database systems, and I'm also going to talk about the advantages of still using relational database systems. I'm not going to throw it down the drain, right? Because there are still some advantages of relational systems, okay? But before I do that, the key challenges is we're talking of different types of data, as we talked about in the variety part. We're talking of agile development today. If you have a startup today, you've got to release your product into very, as fast as you can. Otherwise, somebody else is going to take your space. So how fast can you introduce something? How fast can you introduce your product becomes very critical. Volume data, we already talked about it. We're talking of petabytes of data today. How quickly can you process that? To give you an example, I used to work for Mongo, so I can talk about it from a Mongo standpoint. I was working with Aadhaar. People out here might be familiar with Aadhaar, right? All of you have an Aadhaar card, right? So, and the reason why Aadhaar is one of the most complex implementations worldwide is because the government of India is actually storing biometric data, as you all know, right? How do you store biometric data? Not just normal textual data, but biometric data as well of a billion users. No other country on this planet, guys, I'm telling this out of some conviction, has that amount of data that has to be stored. Yes, China has that amount of data, but as a democracy as well. So the fact that you're talking a billion people and storing that data is a huge challenge. And the UID, they realized that for the profile data, they had to use something other than a relational system. And they actually ended up using Mongo, and the story is different from that point onwards. But essentially, they realized that the answer to it is to move out of relation systems. Okay? So, and it all comes down to these 4 key points. Good.
Very layman question. So when you say the schemas and it's very difficult to add a row or column or
Yes.
whatever. So why people have not? I mean, I have seen people have come out with some proprietary tools which can do that graphically, and then in the back end, you get these modifications done. Why this is not flourished in general?
Yeah, because it's simply because on the one hand, right, let's look at it from just a simple conceptual standpoint. Can I whiteboard it? Is there a pen and paper? So, if I look at a typical database system, right, what am I talking about? I have a database, I have a server, and I have multiple clients. I might potentially have multiple servers, but essentially I'm going to be bottlenecked on what? On a single server. Why can't I have, so the immediate question that you might ask is, in a relational sense, why can't I have 25 databases talking to each other and in a clustered mode? Why doesn't that work in a relational system?
Data integrity. So what?
How do you make sure that data which is across, in fact, it comes down to a lot of different things, consistency, integrity of data, a lot of other questions that you may want, availability as well, right? How do you make sure, in fact, Oracle has something called RAC. People might have heard of RAC, right? Real application clusters. That's a great system, but then it's really about, we're talking about really shared everything. Data is going to be shared across all these database systems. So what am I talking, just coming back to your question, right? What am I talking about here? I'm talking about the fact that this database system that I have, I can make it as powerful as I want it to be, 100 GB, 1 terabyte of memory, but you're going to bottleneck at some point on the server. And once you start bottlenecking on the server, you're pretty much done. So you can't do this whole scaling thing. This is gone. The second thing, and you can use any graphical tool, whatever you want to do, but if I have to change the schema, let's say the data today you're storing is name and age of an employee of your company. Tomorrow you're saying that I don't want name and age, I want something else. Let's say I want height of a person, weight of a person, whatever, random stuff, right? Can you change that on the fly in a relation system? The answer is no, you cannot. So to make those changes in the schema becomes extremely, extremely difficult. And lastly, is it something which is amenable to the cloud? And the answer is no. It's not meant for the cloud. We talked about hardware being very expensive 50 years back. Relational systems were built for a particular purpose, very optimizing for storage. So those assumptions which worked back then doesn't work today. And that's the honest answer to your question. Okay, we'll talk about some more examples, hopefully that will make it clear. Okay, before I completely throw it under the bus, one key thing, and I'm going to NoSQL next. One key thing of relation systems. They are still relevant today. Why? Why do you think it's relevant today? To your question as well. Why do you think the relation systems are still relevant despite all this? Because a little bit of a technical answer as well. Any guesses?
The orderly data will be stored more efficiently.
What do you mean by efficiently?
Storage space.
Sort of, I think, but then
You can reduce the
fair enough, but they can't scale. I still cannot scale, right? So you're right, partially right, but you still cannot scale beyond a point. I'm saying that despite all those challenges, it's still relevant in some use cases. What are those? Let's start with the use cases. Where is it that you're going to still use a relational database system? Well, all of these mostly are OLTP.
financial
Exactly. Why? Why is that? Great point. Why is that?
data integrity.
What do you mean by data integrity? Let's come out of jargon. What do you think is? What do you mean by data integrity?
Transactions.
Okay. Good point. So we're talking of transaction support. Okay. What do you mean by transaction support?
Actually, in those different fields, you
make sure it's very safe.
Exactly. So essentially what you're doing is once, let's say he's kind enough and he gives me some money, right? And I'm going to give that money to him, right? So the point is this has to either happen or not happen. I'm just trying to make it very simple for you to understand, right? Unfortunately or fortunately in the NoSQL world, because we're talking of a scalable world where you're talking of distributed systems, it's still going to be a challenge for you to make sure the data is quote unquote consistent, right? And if you have a problem while you're doing the write, say partial writes or whatever, you should be able to what? Roll back, or you want to commit the data. That kind of a world, unfortunately, is still relevant in the relational world and not, it's still not in vogue in the NoSQL world. There are some solutions coming in this space. We'll talk about that. But still, when it comes to transactions, there's nothing better than a relation system even today.
Actually, in those cases, when you have to, let's say, update again, some particular column of
Okay.
select this ID is,
One particular column you want to.
let's say you have to update it.
Okay.
So in that case, the ID is.
Sure. When data doesn't change that often, data isn't changing, volume doesn't change too much. Fair enough. That's fine. That's okay. But then even there, I would argue that you probably can look at a lot of other NoSQL options because the cost of doing that is going to be very, very low compared to a relation system, right? So partially true, but the key thing is transactions and consistency, right? I mean, you're familiar with CAPS, right? Go ahead.
Don't you have distributed transactions nowadays, so we should handle this?
Distributed transactions? The answer is partially yes. There are solutions coming up. In fact, our company is coming up with a solution. There is already a solution that some of our competitors talk about. The problem is it's still a challenge. How do you make sure that? So the problem is this, right? When you look at distributed systems which are across the globe, there's a system running in Kenya, there's a system running in Delhi, and another system running in New York. Okay, how do you make sure the data which is there across the systems is consistent?
That's where you have the distributed transaction manager which will handle.
You can have any kind of distributed system, and it's still going to have a point of failure, right? So there is still going to be a point of failure. How do you make sure that you roll back something that you've written across these multiple servers that are there? Becomes a challenge. And what point of time? So for example, if I do a write, just give you a very layman example, right? I do a write here, okay? The write is happening here, so it's distributed as still happening, not happened here, for whatever reason, right? If I read the data, should I read it or not? No, right? The problem gets accentuated because we're talking of distributed systems and consistency. And that's a little bit of a challenge. Most NoSQL systems are available. I'm going to get into some jargon right now. People are familiar with cap theory, right? Anybody in the IT space, you've got to be familiar with cap theory, right? We're talking consistency, availability, and what? Partition tolerance. And the fundamental rule out here is you cannot get all three. You can never get all three. Some of you are laughing because you probably have heard it multiple times in your careers. I'm sure you would have. But the honest truth is, even today, you cannot have consistency, availability, and partition tolerance. What does it mean? Most relation systems are consistent, not really available. So if they're partition tolerant, they're not available. If they're available, they're not partition tolerant. So you got to compromise on one of them. You can't have all three. Most NoSQL systems are available and partition tolerant. They're not consistent. Okay, so that's another use case where I would still use a relation system versus a NoSQL system. Okay, fair enough. Let's move on. Okay. All right. So different types of NoSQL systems. Some of you talked of Mongo. Some of you talked of HBase. What kind of a database is MongoDB? What type of NoSQL database? Okay, there are multiple types. Okay, the multiple types of NoSQL. It's a larger ecosystem. In fact, the whole word NoSQL, it's actually a little bit of a, it's a heavily loaded kind of a word, right? NoSQL. Anything which is not SQL is NoSQL, which is kind of weird. Because honestly, the honest truth is, key value stores, column stores, document stores, they're completely different database systems altogether. But they're all branded under NoSQL because they have these some things that they all do, which is like variety of data, volume data, and things that we talked about. All right, key value stores. Any example that you can think of? Redis. Aerospike, guys. Competitor of Redis. Aerospike is another one. We'll talk about that. That's another key value store. What do you mean by key value store? I have a key and I'm going to source of data. The data can be stored in multiple columns. We call it bins. And you can access the data extremely fast. The USP of Redis or Aerospike is speed. I want to do 4 million transactions per second. I want to do 1 million transactions per second. High throughput, extremely low latency. You can only do it with a key value store. Okay, so the data complexity isn't much. I can't store a heavily, sort of a document kind of a, let's say XML type data is very difficult to store because the whole data is stored based on a key and I can access the data based on the key or some of the columns using a secondary index. Okay. The other one is a columnar store. Any examples here? Any examples for columnar store? Cassandra, HBase, right? There are columnar stores. So the USP of a columnar store is, let's say I want to find out the aggregated salary of all the employees of my organization. So in a typical relation system, to be able to find data which is aggregated across all the different rows can be a little bit tedious. In a columnar system, I flip the whole argument across, right? So I wanted to get the data across the entire list of people that I have or whatever. It's very easy to do that. But the problem is, if I flip that around to row-based data and columnar data, it becomes difficult for you to get the data. Right? And in a columnar store like Cassandra, I don't know if anybody's used Cassandra here, but one of the challenges with Cassandra is the footprint, the hardware footprint, and that can be huge. You typically don't hear of a Cassandra use case where the number of nodes are less than 100 nodes. In fact, they talk about, they say, hey, Cassandra is brilliant because it runs over 150 nodes. It certainly is, it works for 150 nodes, but 150 nodes, hardware nodes, the cost of which is going to become extremely, extremely high. So which is why you find a lot of people actually moving out of Cassandra and moving to either Aerospike or MongoDB or Redis or one of these alternatives, Couchbase or whatever. Alright, document databases, example. MongoDB, any other example? CouchDB. So these databases are databases where I want to store data in XML-like form. So hierarchical data, right? Data which has some relationships in there and you want to store it encapsulated within the same object. That's where you would use a document database. The challenge with a document database is, while it's brilliant for storing, it's very simple to use, as people would know with Mongo. The problem is performance. You don't get performance. I can't do, say, upwards of 200,000 transactions per second. It can be very, very slow. So great for content management solutions, great for storing large volumes of data with different types of data, but really poor when it comes to use cases where I have an OLTP system and I want data really, really, really fast. So we talked of n is equal to all, the beer and diaper example. The whole USP there is how quickly can I find association between these data points out there. And that may not be a very strong use case for a Mongo or a CouchDB. Okay? And then a whole suite of hybrids, right? I mean, there's a whole ecosystem of hybrids. There's something called NewSQL. Anyone heard of NewSQL? So NewSQL is coming back to this question about why can't relation systems innovate and do new stuff today? And the answer is they're trying to do stuff where existing SQL, existing relation system, but adding certain features, adding certain availability features, etc., etc. So that's also happening. And there are graph DBs as well. An example of graph DB? Neo4j, right? Titan, Neo4j and all that. Where would you use that? Where would you use a graph database? Sorry? Who's that? Can't see you, sorry. Who said that? Who said? Network, okay. Any easier example than that? More relevant example, social media. You want to make sure that LinkedIn, a lot of you would use LinkedIn out here, right? The key aspect of LinkedIn is, if I search somebody that I want to say apply for a job or get some business out of that guy, I want to see what are the patterns in which I can access this guy. Who are the people who are in between? So let's say it's a third friend of mine, right? How do I make sure that I can reach out to him? So it's all about how quickly can I find the number of hops to this particular guy. So a graph database is really good for those purposes. Having said that, GraphDB is still largely in a R&D phase. I wouldn't say they're still in a phase where people are adopting it in a big way. Okay, so it's still very, very conceptual in some sense, but very, very powerful as well in terms of tooling. Okay? Alright, can you guys see this at the back? Okay, we're getting a little bit of nuts and bolts right now, just to make sure that we understand the concept as well. So people who are not familiar with them, not really hands-on guys, bear with me for a while. Okay? So what do we have here? Guys who agree with this, what is this? What is this table? Can you guys see it at the back? What is this information? What's the information stored out here? Personal information, surname, first name, city, right? There's some information about these people, Paul Miller, all these guys out here. And what's the information out here? Car information. Okay, what are the different types of cars? What's the year, value? What's the person ID? So how do I associate this and this? Person ID. What do you call that in a relation system? Foreign key, right? So whatever the name is, right? So you have some kind of a foreign key to associate this table and this table. This is normalization, right? Agreed? This is a relation way of storing it. How do I store this in a key value format? Okay. How do I store it in Aerospike? Alright. The way you store it in Aerospike is completely different to how you store it in a relational system. And the use cases for Aerospike, one is key value, other one is in memory. I can store the whole data in memory. And the third one is I can store it as a cache. What do you mean by cache? Quick access to data, really quick access to data, because I want to find out what's the product, the stock of the particular product really quickly, and then fire a particular transaction. So how does Aerospike store the information? The recommended approach, in memory, you store the index. What do you mean by index? Okay, person ID 0. Okay, so that's the index entry. It points to the record where this data is. Okay, what is person ID 0? Paul Miller, right? And his car. So the use case is what? I'm trying to find, could be give me all the people who have a Bentley, or give me all the cars that Paul Miller has. Regardless of what kind of question you're going to pose, I should be able to access that particular data point. And the way you store it in a key value store is, I have this key, which is 0 in this case, and it has certain data. So data could be Paul Miller, the city, location, geospatial coordinates. Again, something very powerful in a NoSQL system compared to a relation system, right? Spatial data is a given in a relation system, and you have data which is obviously heavily JSON here, or you have JSON format out here, right? Where I'm talking of potentially map information, right? Where I store Bentley 973 value, and you have a lot of key value stored, key value data within this as well. Talking of all the cars that Paul Miller owns. Fair enough? Makes sense? This is the way this is stored on disk. The actual data is stored on disk. We recommend, Aerospike recommends SSDs because the whole database is built on SSDs. Whereas a lot of other key value stores, they work on magnetic disks, right? We highly recommend that for people not to use Aerospike in a rotational disk, because the whole idea is speed, and you don't get speed out of rotational disk, right? So we recommend storing the actual data on SSDs and the index information in memory. And you can flip it around and say, I want everything in memory itself. That will be even faster, but the cost of memory can be very high compared to disk, right? We all know that.
Where do you do the association ID?
There's no association, right? The whole idea here is normalization. Here I've denormalized the data. I'm showing the whole thing about Paul Miller, which is Paul Miller, London, Bentley, 973 value, Rolls Royce, 965, 330,000, whatever it is, right? That data, I'm storing it in one row itself, in some sense.
But in order to do that, because the data is available in two different tables, you have done some processing before storing it.
Yes, of course. I mean, this is how it was represented before. Now, let's say the use case would be a new guy has bought a car. Let's say you are Rolls Royce, right? And you have a system where when somebody buys a car, you're going to store this information out here, right? So when that happens, there's going to be an entry into the database with the new user and the car information potentially. Let's say you're an aggregator. You want to know what are the different types of cars that you store. So every time you buy a new car, I'm going to add a new entry in this table, in this particular column with the data.
This is in the JSON format?
This data is JSON, yes.
Okay, this,
Data within the map, this is a map,
okay.
that is JSON. I can store it in this, I can store it in maps. I'm just giving an example of one way to store it. You can store it in multiple ways. You could still normalize the data potentially. You could store it like this as well. The only problem is when you normalize, there's no concept of joins in NoSQL. So I cannot say, give me where, person ID is 0, give me all the data.
So, so Aerospike will convert the relation to e-value
Yes.
automatically.
Not really. This is not that I have a relation system, I can transform this and store it there, right? You need tooling for that. If I want to take a relation system and convert it into some kind of a NoSQL format, be it Aerospike or whatever, you need some kind of tooling. It could be a data integration platform, or it could be a migration approach where you take all the data and transform it and store it onto a NoSQL database. But typically, you could start off with a new use case, or you could transform the existing data as well, depending on what kind of use case you're talking
One
about.
more thing, like when you say key values, the key is stored in memory.
Yes.
If you want to search for let's say Paul Miller, you still have to refer to the disk and then
Exactly.
do it.
So let's look at the use case, right? If I want to find, give me person ID 0, I go to memory and get the data.
Then it's
Now, if you say, I want people who stay in London, I want everybody who stays in London, then I create a secondary index, right, on city. And when I have a secondary index, the secondary index data will be here, it points to the PK, and you get to the rows where this data exists. That's how Aerospike does it, by the way. Okay? So you could still create an index on any one of these fields, geospatial fields, any one of them, and get the data looking for, even map data or list data, whatever. And you can get all the data points where this data exists. Okay, fair enough, guys? Got it? We'll get into more details of it, by the way. Okay, this looks great. What format is this? This is document DB. It looks great. I must reiterate. It looks fantastic because it's very similar to XML. I used to work for Mongo, so I know this pretty well. So it looks great, easy to understand because it's it is a document database. But the problem, as I said, is how quickly can I get data? And that's the problem with this. The more complex your data model is, the slower it becomes. Okay. So this is completely JSON. Mongo is completely JSON. There's other examples of OrientDB, CouchDB as well, which is stored in a similar format. But this is again the same thing that we talked about, right? So Paul Miller and his cards, I store it as first name, surname, city, and then you have a cards. It's an array of multiple objects where you store the different cards that you want. Again, here you can create a secondary index, query the data based on give me everybody who has Bentley, for example. You get the data. But having said that, the more the layers inside, the slower it becomes. Okay, so it's a trade-off between speed and ability to store and see data in a beautiful format. So it's stored in binary. In Mongo, it's stored in binary. So it depends on what you mean by text. What do you mean by text file?
I mean, it's basically a sequence of characters. You can store it. It's not stored in some sort of structured way. It's structured through these kind of headers, but it's not like a table form.
Oh no, certainly not TSM. Right? The whole idea is okay. Let's talk about. I think the question is about the overhead, right? So the overhead with the NoSQL system is much more compared to a relational system. Why? Because for every row potentially, I'm going to be storing the key and the data. Every single row, because it will be completely different. The next data point can be first name is 123, for example. It will be a numeric value. So every data point will store the key and the value. Likewise for any other NoSQL system, the overhead is much higher. It can be stored in binary format or non-binary as well. It depends on the different database systems that exist. But you're right. I mean, there is that overhead that exists for every single record. Why is it not a problem? I mean, honestly, the data size or the footprint from a disk perspective can be much higher compared to a relational system. Why is it not a problem today? Storage cost. That's the whole thing we started off, right? The premise is cost of storage has gone down. If it wasn't the case, then NoSQL wouldn't have taken off. It just wouldn't have taken off. Okay? Got it? Alright. Okay, this is again getting back to technology, guys. Okay, so people who are not interested in technology can take a little bit of a nap. Okay? I'll just talk about Aerospike. Go ahead. Yeah, can you be louder, please? Sorry.
What is that? For instance, suppose I wanted to change the format.
Yeah.
Or the number of the maximum possible length of name.
Okay, sure. Maximum possible length of the name.
Of the name.
Okay.
Maybe previously in the relational database, you might say that it can be a maximum of 50 characters.
Okay, you have a constraint which says give it should be 50 characters. Okay.
In this context,
Yeah.
for instance, for the key value,
Sure.
are going to have similar limitations?
Sure. The answer is no. Simple answer. There is absolutely no limitation or no constraints on the data. This is not just a key value store, any kind of a NoSQL data, most NoSQL databases. Okay. This size of a particular column or a particular field, whatever you call that in the different NoSQL systems, the only constraint that's imposed is it cannot exceed, obviously cannot exceed the size of what? Of the record. So in Aerospike, for example, the maximum size of a record can go up to 1 MB. In MongoDB, it can go up to 16 MB. Okay, a lot of other databases go 2 MB, whatever be the size. You can never have this field exceed that, obviously, right? Because it's part of one record. But there's no limitation that's imposed on a particular field. In fact, the whole idea of NoSQL is its simplicity. Why did Google take off? It took off because of the simplicity. And that's the whole idea of NoSQL. It's very simple. We'll just do a quick exercise as well. You'll find it's extremely simple to do. And that's the biggest USP of it. Good. Okay. Alright, so, okay, let's quickly look at the concepts, guys. Very quickly. We'll do an exercise as well. And this is Aerospike land. Okay, I'm talking of Aerospike land. Alright, so the biggest USP of Aerospike is, if I want the data, let's say I want the data. Okay, let's say, I'll give you an example. Let's say this is one server and this is another server. Now I'm looking for a particular guy. Let's say I'm looking at him. So what's your good name? Rajendra. Let's say I'm looking for Rajendra. If I were a MongoDB, if I want Rajendra and there are two servers, what I would do is, in most cases, I'll ask another guy sitting out there. Let's say there's some hypothetical guy out there. I'll say, hey dude, where is Rajendra? and he's going to say, Rajendra is here. He's going to point me here. And then I say, hey guys, give me Rajendra. And Rajendra is given to me. Okay? That's the Mongo world. In the Aerospike world, I am let's say, in some sense, a super user or whatever. Call me as a thick client, in other words, the thick client. So I have information of where to go for what information. I want Rajendra, I know how to go here. I want, what's the name? Okay, I want Vineet, I'll go here straight. The client knows where is Vineet, and the client knows where is Rajendra. How does he know that? He knows that based on the key itself. So in this case, like example I gave you, Vineet and Rajendra were the keys. And the key is mapped to a hash of a key. Familiar with hash, guys? Okay, hash is nothing but, in some sense, creating a randomized value for that particular key. When I randomize a particular value, the data is going to be distributed across these two things, right? To this server and this server. So in some sense, I'm creating a distributed system where I'm not compromising on speed. Because I'm going straight to the data and I get the data I'm looking for. Got it, guys? Okay. The second thing is, what I talked about was the smart client part, sorry. And the second thing is, there's no hotspots in the system. What I mean by hotspots is, there's no one guy who's ruling the roost. Okay, everybody owns some part of the data. This server owns all of you. This server owns this set of data. And both of you have equal amount. In fact, it's actually the case right now in the room as well. The data is distributed across the two servers. What happens in a Mongo is something different. In a Mongo, they have a concept called shards. Okay, somebody who's used Mongo would know. And in a sharding concept, what happens is there's a primary and few replicas as well. What does that mean? Is this guy has a replica who is possibly there outside another room. So if these set of people are this goes out or this is down for some time, I point to that guy. That guy has no role to play unless and until these guys go down. That's not the case in an Aerospike. In an Aerospike, every one of these servers owns some part of the data. Okay? So your replica, the exact replica of all you guys, is stored here as well, and their replica is stored here, in this example. Okay? So every one of the guys owns some data, and there's no hotspot. If one guy goes down, it doesn't matter. There's absolutely no hotspot in this whole system. It's easy to scale. Make sense? Alright, so all the systems are shared nothing systems. Go ahead. Sorry?
Is it replicated?
Yes, it's replicated by default. In Aerospike, the replication factor is 2. In a Mongo, the replication factor is 3. Which means that I have 3 copies of the data. In Aerospike, we recommend just 2 copies of the data. It's replicated by default. You can turn it off if you don't want, which is not a great idea.
So both of these uses like Hadoop like distributed file system or it's a different proprietary distribution? Both of these architectures like Mongo and HBase, they use Hadoop distributed file system?
No, we don't use Hadoop. So only HBase does. In fact, HBase also does it. Yeah, using Hadoop if it wants to, but in our case, we don't use that. So, for example, in SSDs, we use a file system where we can store the data in SSDs.
And that's distributed.
Yeah, whatever it's distributed as well. Yeah, it's a different solution.
Can you please repeat this?
Yeah, what I was trying to say was, from a file system standpoint, we use the file system which is available. So it's not dependent on a particular file system.
So it's not Hadoop, you could use Linux based or Linux based.
Whatever file system is available in that server that you have. Right?
But
Having said that, when it comes to SSDs specifically, we have built our own file system to make it very optimized. So you don't have layers in between, the RAID log, the SSD controller, all those layers are not. You go directly to the data which is stored on disk.
Hadoop specifically warrants large data access, right? So in your case, that's not the.
Remember, Hadoop and we talk of the at the end, Hadoop and NoSQL are completely different systems. Hadoop is where you're talking of an offline system. I want to process large volumes of data. Massive volumes of data, understand patterns of information out of that. There's no user sitting out there. There's no user sitting out there looking at whether my ticket was booked or not. And I think you mentioned the point of OLTP or you guys mentioned OLTP versus data errors. So the concept is different. Whereas NoSQL typically falls in the OLTP bucket. You have a user sitting out there, he wants to make sense of the data, it has to be real time. Hadoop need not be, it's completely backend, it happens on its own place. That's the difference between the two. This is more storage, that's more processing in some sense. Good.
How is it different from Mongo's data guard?
Yeah, sure. So data guard, and we'll talk about the context. Just give me a minute before I come to data guard versus replication. Okay, guys, just be with me for a minute here. Okay, so what are we talking about here is, so you can see here that there are multiple servers out here. I'll give the example of this multiple servers being there. And the whole idea of this is the clients connect to the servers, all the servers. If one of the guys goes down, what happens? There's somebody else who has the same data. You point to that guy and he gets the data. So you have resilience built into the NoSQL database. Regardless of which NoSQL database you're talking about, there is availability built in. It's by default. It's running all the time, and you can always point to another guy who has the data, right? In DataGuard, one, you have to build a new solution. You have to buy a new solution for DataGuard, okay? This DataGuard is active DataGuard. If you want active, you have to buy a solution. And second of all, you're talking of an overhead. And the overhead is, you're having one server containing data, another server sort of a DR for this guy. So if this guy goes down, then you point to this guy. So other guy has no role to play.
But let's suppose give example of Exadata.
Yeah, sure.
So within Exadata, there are 2 or 3 copies of data.
Sure.
You want to specify 2 copies of 2 copies.
Sure.
So it's running within the server, but suppose if the hard drive goes down, then the data in another disk, that is the copy of the data, that will come up on the data disk.
Yes, but again, you're constricted by the fact that you're talking one single server. If I want to distribute it, what happens if the Exadata box goes down? Same problem, right? That's what I'm talking about. Here I'm not constrained by any single server. And remember, when I talk of server, this is another thing very important. I'm not talking of a costly thing, guys. I mean, we're not here, most of us here are going to end up in some startup or some kind of a smaller company, right? You're not going to buy an Exadata box. Right? And if I was a sales guy, I wouldn't be talking about this at Oracle, but the honest truth is, nobody's going to spend $1 million for an Exadata box. You're going to talk of some kind of a cloud instance at a very low cost and start off from there. So I want something which is extremely easy for me to scale. At the same time, if I'm going to grow, say, at 250% over year on year, I should have a system which can scale out easily. So the whole concept is completely in terms of different to what an Exadata box can do. So Exadata box is great in scaling up. It's brilliant in that, but it cannot scale out. Okay? Alright guys, so I'll look at examples just to make it more clear. So there's no single point of failure. We do something that based on, we partition the whole system and we say, hey, each of the partitions is owned by one guy. So everybody owns some partitions, and there's a way in which this is figured out. Okay, so everybody figures out. We use something called Paxos, just for technical enthusiasts out here. We use Paxos to figure out who owns what. Okay, and it's also a way in which you make sure that everybody is in sync in the server that you have there. Okay, in the cluster that you have.
Sir, I'm going to be a bit confused here.
Yeah.
The copies that you told about.
Yes.
Will it be within the server or will it be distributed across the server?
Sure. So same example, let's say Rajendra, right? So Rajendra's data is going to be here, and it's also going to be here. Vineet's data is going to be here. It's going to be here. Okay, so I make a change to Vineet. Let's say I add skill set, some new skill set. Let's say NoSQL. I go here. I make a change, skill set update to NoSQL. That gets replicated here as well. So the other server has the same copy of the data at real time. Got it? So every guy owns something as well as is a replica for the other guy as well. Okay, we look at an example. This will become more clear. Okay. So the whole idea here is data is going to be distributed randomly. It's going to be distributed randomly. Everybody owns some part of that. We talked about this. I won't spend too much time. We use a algorithm called RIPE-MD 160. Okay. So this is a conflict, free kind of algorithm that we use, hashing algorithm. What it does is for every key, so for Vineet or for Rajendra or whatever, there is a key that's the hash key which is calculated, and this is the unique value is 2 to the power 160. So it's going to be unique any which way. And it's going to come up with a key. So for example, this key that you have here, it has a hash value which is this, and this hash value is going to map to one of the 4096 partitions. Each partition is going to be owned by one guy, and the replica copy is going to be another guy as well. Okay? I know I'm getting into too much of stuff, but we'll look at an example where this becomes clear. Okay? Alright, the example is this. Simple example. Application has a client to the NoSQL database, in this case Aerostrike, and I'm going to write some data. Let's say data I'm writing is about Rajendra, right? So I write the master copy and then replicate it onto node B. Fair enough? Now I want to write some data about Vineet. So I write about Vineet and I replicate the data. Replication happens within the database. So to your question, what's your good name? Sorry. Vivek, your question. This is the entire database landscape. It happens within the NoSQL system. The application doesn't have to worry about who is replicating where and all that. It's inside. It's abstracted to the application tier.
Yeah.
So he takes care.
The solution is on application.
Yes.
Yeah. So my question was that if we are replicating the data across the servers,
Yes.
so that we can do an Oracle system, like take some random server.
So the question is this: if I were to have this kind of an Oracle database configuration, node A, node B, node C, I want to fire a query which says, give me Z and Y. Join. I'm using a join. What will happen to the query? What will happen to the query? So you have two tables, car and people or whatever. People is here, car is here. Or the corresponding entry for car and people is here. What happens to your query? Answer is going to die. It's going to be dead. It's going to take you enough time for you to go down to IIMB to the main road and come back and assume you won't get the answer, right? Because you're talking of two systems where data is distributed. The whole idea of joins in the SQL system is built on a single server where you can access data. So it's you can't have both, guys. You have to take a stance, right? In the relational world, the stance is I'm looking at consistency of data. I'm going to look at a single server. It opens up a paradigm, a completely different use case altogether, right? If you're talking multiple servers, consistency will go for a toss. Okay? When consistency goes for a toss, the only option you have is availability. So that's where the new SQL kind of systems are coming in. They're saying, no, let's keep SQL, but at the same time, let's make it a little bit like NoSQL. Okay? Make sense, guys? Got it? Alright, so that's just an example out here. Okay, let's look at how it works from a concept perspective and go straight into an example of this, okay? In the interest of time. I know we have 30 minutes now. Okay, so let's say this is, okay, I'll make it simple here. This is a set of partitions, okay? 4096 partitions. A partition is nothing but, this is one partition, let's say, and this is another partition, okay? Instead of servers, let's look at partitions. Now this partition is owned by A. Let's say it's owned by this room. This set of guys are owned by this room. And the replica is the other room. Let's say C105, whatever the room number is, right? Whereas your set of guys, the main set of guys, are in 105 and the replica is in this room. That kind of an example, essentially. Okay? So if you look at it from a server perspective, I look at the server A, this room. I have a master copy of this and a replica copy of you guys. Okay? Likewise for B, I have two which is a master and one whatever partition that is, the data which inside that partition is stored this way. Make sense? Okay. So what happens when a node C goes down? This is the power of a NoSQL system, not just Aerospike, most NoSQL databases. What happens when C goes down? What happens to the client? The client is connecting from here, right? He's trying to connect. He was trying to, so whenever he had, let's go back. So if you wanted to make an update for 3, where would he go now? Where will I go if it's, where's the master copy of 3? C. Yeah. So he's going to go to 3, he's going to go to C. If I want to make an update for 1, where would I go? Okay, this is understood, right? What happens to, when I make an update to 3, what happens? It replicates to A, right? So far so good, right? So now if C goes down, where does the client connect to? Perfect, right? Because A has the replica, this becomes the master, and a replica is going to be created in B. Because only 2 servers remain. B will start owning or become a replica of 3 as well. Obviously, all the migration of these records which exist here has to happen from A to B. Okay, just an example to make it more clear. Yeah, so essentially what happens is, let's say look at 6. 6 essentially what happens is, yeah, so in this case what happens, the colors are really weird here, but let's look at it like this, right? Okay, so you're going to have a master. What happened in the previous one? Alright, so what's going to happen, this is not correct actually. What will happen is 6 becomes the master here, and the replica is going to be this guy. Okay? Because he was the replica before, so he has the copy of the data, so he becomes the master, and this guy becomes the replica. Okay, you got the concept here, right?
What if suddenly C comes up?
Yeah, that's a good question. So that's a brilliant question actually. What he says is, what happens if C comes up? What do you think should happen? Let's look at the behavior.
Which will inform not central entity that now I have to.
There's no central entity here, guys. Our whole idea is distributed systems, there's no central guy. Because the central guy is going to become the point of failure.
system remains as is. Now A has become the master, it remains the master.
Okay.
We start utilizing C.
Okay, that's one option. So the answer is, if C comes back up, we're going to go back to the state. The same state which existed at the beginning.
Data beginning.
Assuming that
Hold on. Okay, this is where we're going to go to eventually. What happens when C comes back up is, let's say we look at 3. Okay, when C was down, who was the master of 3? Okay, A, right? So any updates or writes that happened for that particular partition would exist in A for this particular guy. When C comes back up, he has some copy of the data. So what should happen is, whatever updates happened to 3 during the time he was down needs to be migrated to this guy, and he actually owns the data from that point onwards. Even before the migration happens, any new updates that would happen is going to happen to this guy. Any reads that might happen, if he doesn't have it, might be proxy to this guy. He might still proxy to the guy because he has that information. Make sense?
There's a replica also, right? So before the C comes up, there's a replica also created.
Yes, this is going to drop off. If you have a replicate factor of 2, this guy is going to drop off. If you have a replicate factor of 3, he might still exist even after that. Good.
So you mentioned that there is no central guy.
Yeah.
So who is keeping the partition map?
Sure. The partition is a great question. Who is keeping the partition map? The partition map is kept by every one of the servers. So in this case, A, B, and C, who actually come up with the partition map. Okay, they decide on the partition map. It's a consensus of an algorithm. They decide at the very beginning, based on the node ID, what is this partition map. Okay. This partition map every second is sent to the clients as well. If I have a Java client running, the Java client also knows what's the latest partition map based on the version ID. There's a version for the partition map, and every one of the servers and the client knows about this partition map. Okay, and that's why they know. Okay, in case, let's say, in case where the client is back by a few versions, in which case he might go to a wrong server, but that server will tell you, hey, you're back in terms of the partition map, but now I can proxy you to the other guy who actually owns this data. Go to that guy.
What is like this, like Hadoop world, we have a game node, there's nothing like we have here at all.
In fact, in Hadoop world also now you don't have a single point of view. The whole problem with the name node is that what happens when the name node goes down.
Yeah, like backup, right?
Now you have federated name node, there's a lot of other concepts that are coming. You don't want a single point of view. The biggest problem of Mongo, right, is, and honestly, well, a lot of great things with Mongo, the biggest problem with Mongo is you have a single point of failure. What is a single point of failure? It's something called a config server. You use that in Mongo? Okay, config server is basically the storage of metadata. Okay, I told you, right? There's a guy out there who's sitting out there. He's going to tell me where is Vineet or where is Ravinder. He's going to tell me where is Vivek. So what happens if that guy goes out for a coffee? I have nothing to do. I don't know where to go to. You won't go randomly and ask people, right? Because there's no relationship between you two. You have no way in communicating with each other. Okay? So that's going to be a problem. Okay? So you're creating a single point of failure which is not required. And that's what Aerospine and all these other uses in newer database, NoSQL databases have done. There's no single point of failure.
Does it work in form of instances and different servers?
So each server will have its own instance. You're right. So every one of these guys has its own instance. How do they communicate with each other? There are two ways in which you can communicate with each other. One is multicast or unicast. We'll set it up and I'll show you how it works. Okay, so clear with this concept, guys? So when the server goes down, you point to the new guy and it just comes back up as it is. What happens when a new node is added? What do you think should happen when a new node is added? Let's say D is added. What should happen then?
Partition map is.
That has to update.
Okay, it should get updated, but in a current state, everybody owns all the partitions, right? What should happen then? Redistribution. Okay, so obviously new partition map. This guy is going to own some copies. It's going to be a replica for some copies, right? Okay, can you tell me how many copies? Let's say 4096. How many partitions you have to migrate to this guy? Who can work out the math very quickly? So let's say 10 nodes. Let's make it simple. Let's say 10 nodes. Can somebody tell me if it's 10 nodes and 4096 partitions? How many partitions have to be migrated to this guy if he comes up? Okay, how did you get that? Yeah, because you're going to be having the copy and a master data. So that's the number of replicas, the number of partitions that have to be migrated to D. Okay, in this case it's 4 nodes. What's going to happen in the meantime is any query that comes, let's say 12 is owned by D. Any query that comes to 12 might actually proxy to this old guy, right? And the guy who actually had the replica might drop off. He might drop off the copy after the migration completes. Okay? So this is exactly what I'm talking about, and it works beautifully that way. All right, so let's look at one quick thing before we do an exercise. Okay, again the same thing. The question is, where would I use Hadoop? Where would I use NoSQL? I hope you got some clarity in this. We're talking of real-time use cases, a user sitting out there, online use case, and this is more offline. I want to crunch the data. So they're completely two different domains. In fact, I have had customers who come to me and say, can I run Hadoop in a NoSQL system? The answer is no. They're completely different areas of work. You need both of them, and both of them need to coexist. How do they coexist? Using some kind of a connector. You can push and pull data from Hadoop onto NoSQL or back towards Hadoop. Okay. It can also be Spark connector, real-time Spark connector, or Hadoop connector. Either one of them. You'll have it with most NoSQL systems. Okay. Fair enough. Any questions, guys? I want to do a quick exercise. Yeah.
Those records, right? There is a maximum size for each record.
Yeah.
And then you would not be occupying that entire space, right? So the record will be smaller and larger.
Okay.
But when it grows, then how does it align?
Okay. Let me answer that by two parts. Okay. The question he's asking is, what happens when the block of data isn't fully occupied? Okay. Is that the question? And two, what happens when the data grows? Okay. I'll take both examples. One is of Mongo, and another one is of Aerospike. Mongo, how does it work? Mongo, there are two storage engines. One is called WireTiger, and another one is called Nmap. Okay, look at Nmap. We look at Nmap, and then we come to Aerospike as well. Okay. So Mongo, what happens is when you write a block of data. Let's say you wrote a block of data. Okay, and obviously, let's say it is 64 bytes. Byte is 64. I mean, a block is 64 bytes, and the next block might be 128 bytes. Okay. Let's say the amount of data written is 38 bytes. So you obviously have some free space here, correct? You have around 26 bytes here, right? So if the data grows to 64 bytes, you are going to grow the data with it. It's called an in-place update. Okay. So there's an advantage to this, that your storage footprint is going to be reasonably, efficiently used. The downside to this is what? Updates can be very, very slow. Okay. So this is how Mongo's Nmap used to work. Okay. This is how it used to work. Now what happens with, so the other point is what happens if it grows beyond 64 bytes? In which case the data has to move to the next 128 bytes thing, and it's going to occupy this block here. Okay, and the reference to this guy is going to be removed, and this is going to be deflagged. Okay. Likewise in Aerospike it's completely different. We use a log structured file system. Okay. What it means is, and this is similar in terms of a lot of other NoSQL databases. I do a write. Okay. By default it is 128 kilobytes block. When I do a write, let's say it is, I do multiple writes. Each of them are multiple blocks. Now, what happens in the next update that happens? Let's say for this record, I make an update here and dereference this guy. So it can be an update which increases size, decreases size, whatever, it doesn't matter. Okay, so I'm just going to dereference this guy and create a new one. So logs
It's a new place that it goes.
yeah, new block. Yeah. And this can be, you can defrag that, you can make sure that you optimize for storage. Okay. Any other questions quickly before we move on to the next exercise? You know what? Have you guys tried to install Aerospike or Mongo? Anyone if you have? I'll show you a quick demo, so it doesn't matter if you haven't. You can try it out later as well. Okay?
It's in Maven and
Yes,
GDK
yes.
and
That's right.
the demo that's in
You've done it?
I mean, not Mongo, but Mongo needed that.
Mongo, you don't need that because Mongo, what happens is all you need is the MongoDB. Okay, that's fine. I'll just show you guys. Don't worry. I'll show you both of that, and you can quickly play around with it as well. Okay. So let's see. All right. So I have 3 servers that I have. This is on AWS. What I've done here is I'm going to show two things. Okay. I'm going to show you a cluster configuration in Aerospike, and then try to do some Mongo stuff, and then we'll do some CRUD operations on top of the database. Okay, and I'll show you how failover works. Okay, so how do I set up a cluster? I've shown you the part where you download the binaries from the website, right? Aerospec binaries. Just download the binaries, set up, install it on the 3 servers. As soon as you do that, I need to probably the network thing will go on now. Okay, while this connects, let's do a quick Mongo stuff, okay? Okay. So Mongo, how do you run it? Is I run something called MongoD. MongoD is a server. Okay, this is a server, and I started off. So Mongo is great when it comes to single server. Okay, it's extremely easy to set up a single server. Now server is running, and what I do is I create a client. In this case called Mongo. This client talks to the server. That's it. Just install the binary of Mongo, start the server, go to the client, and let's say I can do show DBs, right? So there's a database called test, there's a database called local. I can say use test, which means I'm going to use this database. I'm going to say db dot, I'm going to create, so a table, nothing but a table. In Mongo they call it as a collection. Okay? db dot call dot insert, let's say I want to do an insert. This is just a test client, okay, when I'm doing this, it's called Mongo. And let's say I'm going to insert a document, right? I'm going to insert a document where, say, institute is IIMB, and let's say, ID is 25. Okay. Now, what happens in Mongo is when I insert it, I can also do a find. Okay, so forget the other ones, but essentially what you have is it creates its own object ID. This is the PK in some sense. I can use that PK for storing this ID, and I have some data. So you got it, right? I can store extremely complex data, and this is a single server. I can do it in my replicated mode as well. Okay. All right. You got it? Got it, guys? Extremely simple to create. Yeah, there's no local machine. There's no schema, nothing that I defined. I just said use database and start pushing data. So I can also say the next one can be completely different. I can completely remove these fields and just do it without anything. Okay. That's it, right? So I can say there's one thing without anything, without any data. So there's no schema. That's the whole idea of any NoSQL system. Absolutely no schema. Okay. I'm just going to show you replication as well. So hopefully I can copy. Let me do a quick SSH. I'm hurrying it a bit. If you guys have any questions, make sure you ask it. Okay, so I've connected to 3 AWS instances. Okay. Now what I'm going to do is, there's something called a config file in Aerospec. I hope you can see this. See the very bottom. Let me just go through that. Okay, can you see it, guys? Okay, so there's a config file. The config file has certain information, okay? Forget all this information. There is things like, what kind of users can use it, what some number of threads and all that stuff. Forget that. All you have to change is, in a section called network, there is something called heartbeat, okay? In the heartbeat section, if I'm using mesh, all I have to give is a seed port through which, seed IP address and port through which I'm going to connect and create the cluster. In this case, I have given the same IP address for the 3 servers on all 3 boxes. That's all. I do this and start the server. That's it. Finish. Your replica environment is set. So just to show you, there's a tool called ASADN. I'm going to start this. And what it tells me is, there's a lot of wording here, but it tells me there are 3 servers. Okay? The server 1, server 2, and server 3. Can you see this? How many copies of the data I have? 2 copies of the data. Okay, there are multiple. So in Aerospec's case, a database that you saw in Mongo, for example, is called a namespace. Okay, a set or a table is called a set here, a collection in Mongo. The jargon is all over the place, but essentially this is the information that you have. Okay, so what happens is, let me show you an example now. Okay, So, are you guys with me? Okay. So let me show you who owns what. Okay, this just gives who owns what. Actually, the partitions, right? The partition map. This tells me that for partition 1 is owned by a particular guy. In this case, he is the owner. In some cases, he is not the owner. Okay. In some cases, he doesn't even have a copy of the data. So every one of the partitions is owned by one guy, one of the 3 nodes, and there is, the replicas as well. Okay, this gives you the partition map.
Which one shows that this is a replica?
Yeah. So the replica is 1 here. You can see this one. This is the replica. So this guy is the replica. The node that I'm looking at right now, he's the replica. So let me show the same command in the other guy, in the other server. Okay, so the same command. Okay, so you can see this now, right? The same partition 0. Look at 0. 0, this guy doesn't own it. So that's why it says A. Okay? Whereas the other guy, if I go to the other server, it says S0. So he owns it. He is the master for this particular node, for this particular partition. Yeah, that's what it says. Okay. So let me just show you a quick example. Let's use a tool called AQL. There's a tool called AQL, similar to SQL, where I can say show sets. Okay, show namespaces. Okay, so there is 2 namespaces, test and bar. I'm going to say this is very similar to SQL, so I can say insert into test dot, let's say test dot test. Okay, test dot IIMB. Let's say name ID. Okay, values. Test name. Okay, just give me a second, guys. Okay. Just this. I need to do a ID. Okay, let's leave it like that. Okay, so now if I select star from test.imb, pk equal to key1. Let's look at that. Oh, test.mo, sorry. Okay, so you got this data point. I told you that this data is the primary key information is not stored on disk, it's only stored in index. So I've got this data, the name and ID, right? So this is owned, let's assume that this guy is owned by this particular node, okay? Let's assume for a minute. Now, if I go to the other node, if I say the same thing here, I can see this data everywhere, right? Data is available everywhere. Whenever I query for this, I can get this data. Now what happens if I kill a server? You still get that because it's there everywhere else, right? So that's the whole idea. Somebody owns it, but somebody else also has a replica. It happens real time. This query and update happens real time. Okay? Alright, one last thing. Let's go to okay. So there's one more demo that I sent you guys. Enthusiasts can look at that. The demo is called, it's called time series demo. I must have written that. So it's a very interesting one because it's very relevant in terms of use case. What I've done there is, in the demo, is I've taken financial data, and what I've done is you can name the stocks, which stocks you want. Let's say you take 5 stocks or 10 stocks. Let's say I'm a guy who's investing in stocks. I want to see what's my stock position, where am I at right now, which stock is the best, which stock is the worst. Give me the top 5. So there's a concept in Redis and Aerospike where I can do sorted maps. It's a data type. So it will sort the data based on the map data. So the guy with the best value is first. So it's ascending order, descending order, you can get the data that you're looking for. The top and bottom values and stuff like that. So if I run this, I'll just finish this and then we can wind up. Alright, just go to the website as well. Okay, it has the instructions as well. So all you have to do is run this. There's some instructions out there to make it work. So let's run this. Obviously, I'll change the server. The server IP address is 54.159. 54.159 dot. So I can give any one of them. 249.2. 249.2. Okay. So what am I doing here? I'm running a particular this demo jar file, and I'm saying load it and read the data. The stocks are, which is this? Apple, IBM, Oracle, Microsoft, Cisco, and this is the server IP. Give me the data for the last 2 days. Hopefully it will work. Okay, it's loading data now. It's taking data for Apple. This is Apple for day 1, I think.
But this is happening only for the server too, right? Not for the databases on the reference.
No, every server. It connects to every one of the servers. It basically connects to the cluster. So the insert will happen to the respective nodes. I think that the network is very slow. It's very fast actually. Run it in your home, you'll find out. I think it's extremely slow. So what it does is, it will take all the data, it will insert the data into the database, and then it will give the stock position. I don't know if my internet is working.
So what is equivalent to a map?
Sorry?
What is equivalent to a map?
You can actually run MapReduce jobs even here. In Aerospike, you can run MapReduce jobs.
Because he is also doing some sort of aggregation like sorting and tracking.
No, here I'm not doing any aggregation actually. Interestingly, I'm doing no aggregation here. It's from the data itself, I'm finding which is the best stock position, which is the worst.
So generally in other places you have to do some aggregation.
Yeah, if you want to do aggregation, you can use MapReduce. So MapReduce, what it does is each of the nodes, similar to MapReduce, it will run a map and then a reduce the function to get the data that you're looking for. So you can run an aggregation function to get the data. In Mongo, there's a different framework. Mongo has its own aggregation framework as well. You can also run MapReduce, but there's an aggregation framework that Mongo has written where you could get the data that you're looking for. Yes, most of the NoSQL databases have a MapReduce framework that you could use. Okay, so this is very slow. I don't know what's happening, guys. So what I'll just show you what you get. You can try it at home. So what you get is something like this. I think the network is down. Okay, so what you get if you run that is something like this. Okay, you get the top. Essentially, you get something like this. Top position like this. Okay, you get the top 5 stocks. And then for each stock, you'll get the beginning value, end value, and the difference between the two. So this is time series data, right? I mean, obviously time series data. And you can store time series data in a NoSQL system. It's very powerful. There are some specialized time series databases as well, if you want to try that out. But there are a lot of options out here. Okay? You could use any of them depending on the use case. Alright, just to summarize, I won't take more than a couple of minutes, very quickly. So the point is, in a NoSQL system, just to, sort of, the net is this. Depending on the use case, look at the database of choice for your use case. There's no one size fits all. Okay, Aerospike has a use case in certain areas where it's a great fit. It may not be a great fit in certain other areas. Likewise with Mongo, and same with relational databases as well. It works in some cases, it may not work in some other cases. Okay, but this is an extremely hot area to work in. It is an area where there's a lot of adoption right now. Financial services companies are adopting it in India. One of the most conservative banks in the world is starting to move towards NoSQL in India right now. And this is happening at a rapid clip. So folks who are interested in NoSQL as a career or want to get into technology parts of NoSQL, this is an area to be. Likewise with Hadoop as well. This is the area where you'll see a lot of innovation happening and a lot of adoption as well. So depending on what kind of careers you're looking at, be it in sales or engineering or whatever be the areas, this is a very hot area to look at. And if anybody is interested in a job as well, feel free to reach out. My card is here. We are also looking to hire people as well. So anybody who's interested in engineering or pre-sales or sales, reach out to me. Okay. Any questions on NoSQL or database systems? Anything else?
Just one thing. So, if have you guys done the benchmarking of Aerospike with MongoDB?
MongoDB, I mean, there's this one benchmark, but MongoDB we don't do much of benchmarks because MongoDB is not known to be very fast. We've done benchmarks with Couchbase, we've done benchmarks with Redis, we've done benchmarks with Cassandra. It's available. Just search for Cassandra, Aerospike, you get a lot of benchmarks. Okay. Any other questions, guys? Any more questions? Last questions? No? Good? Alright, thanks guys. Any questions, feel free to reach out. My email ID is there. Happy to take any questions that you have later on as well. Thanks for your time, guys.
Thank you.